Abu Rayhan Muhammad ibn Ahmad al-Biruni was born in 973 CE in the region of Khwarezm, a cultural crossroads seated between the Iranian plateau, the steppes of Central Asia, and the fertile banks of the Amu Darya. Khwarezm in the 10th century was neither a provincial backwater nor a singular imperial capital. It was a mosaic of influences, Persian, Turkic, Sogdian, and Islamic, interacting constantly through trade routes that tied the region to Baghdad, Bukhara, and even the far steppes beyond the Oxus. This geographic placement gave Al-Biruni a childhood surrounded by movement. Merchants passing through with silks and spices, astronomers discussing celestial patterns under desert skies, and scholars carrying manuscripts written in languages that coexisted uneasily, yet productively. His birthplace was therefore more than a location. It was an environment where cultural exchange formed the atmosphere of daily life. Khwarezm, at the time of Al-Biruni's birth, was ruled by local dynasties who valued scholarship as a marker of prestige and governance. Libraries and observatories, supported by court patronage, existed not as ceremonial symbols, but as working institutions where inquiry was encouraged. Young Al-Biruni grew up hearing discussions of mathematics, medicine, theology, and astronomy, not as abstract theories, but as practical tools used to measure land, survey the sky, and calculate the calendar. The region's scholars read Greek works in Arabic translation, preserved Persian sciences, and interacted with Indian and Central Asian intellectual ideas long before Al-Biruni crossed into those lands himself. This early exposure shaped his mind toward universality. He learned not to prize one civilization's knowledge over another, but to treat all knowledge as part of a single vast network waiting to be mapped and compared. The physical landscape of Khwarezm also played a silent but decisive role in forming his observational genius. Wide horizons allowed the young Al-Biruni to observe stars without obstruction. Deserts offered clarity of sky, and the nearby river delta showed him the interdependence of climate, agriculture, and settlement. His earliest scientific curiosity likely grew from watching seasonal floods, shifts in wind and temperature, and the movement of celestial bodies that governed agricultural cycles. Such observations were not merely poetic impressions. They cultivated in him a habit of linking natural patterns with mathematical structure. The rhythms of Khwarezm became his first classroom, teaching him that every phenomenon has a measurable cause, and that understanding requires patient, precise attention rather than speculation. Khwarezm's intellectual climate, rich but contested, further shaped his early worldview. Rival dynasties competed for cultural authority. Scholars debated religious doctrines as intensely as astronomical theory, and translation movements brought foreign knowledge into Arabic scholarly discourse. Al-Biruni witnessed firsthand how ideas traveled and transformed, how Greek geometry could coexist with Islamic theology, or how Indian astronomical models could be compared with Ptolemaic systems. Rather than confine himself to one tradition, he developed an extraordinary openness that would define his career. His birthplace gave him not only literacy, but plurality, a mental structure in which knowledge could be questioned, verified, compared, and synthesized. By the time he reached adolescence, Al-Biruni was already positioned at the center of a world where learning was both a privilege and a responsibility. His early environment in Khwarezm did not merely give him tools, it gave him perspective. Surrounded by multiple cultures, diverse languages, and a landscape that demanded scientific attention, he formed a lifelong dedication to observation over dogma measurement over assumption, and curiosity over certainty. His later work in astronomy, mathematics, geography, linguistics, and comparative religion would reflect this foundation. A childhood shaped by the openness of the steppe sky and the convergence of civilizations flowing through Khwarezm like the river that sustained it. From the earliest years of his life, Al-Biruni displayed an alertness that set him apart from those around him. While other children played without concern for the world beyond their village streets, he is said to have watched the movement of the sun's shadow, traced the arc of the moon across the night sky, and asked questions about things adults considered ordinary. His curiosity was not a momentary impulse, but a persistent force. He wanted to know why birds migrated, how seasons changed, what caused a shadow to lengthen at evening and shrink at noon. Instead of accepting inherited answers, he tested them through observation. This early insistence on proof over assumption foreshadowed the scientist he would become, a thinker who trusted measurement more than tradition and inquiry more than authority. His natural intelligence showed itself in the speed with which he grasped numerical relationships. Where his peers memorized multiplication tables by repetition, Al-Biruni seemed to see patterns within numbers, the regularity of squares, the scaling of geometric ratios, the hidden rhythm of days and degrees. He quickly understood that the world around him followed numerical order, even if people lacked the tools to describe it precisely. Clay jars, filling and emptying with water, the circular spread of ripples in a canal, the consistent spacing of stars at particular angles, all of these became experiments in his young mind. Knowledge, for him, was not an abstract inheritance. It was a puzzle waiting to be assembled piece by piece through careful attention to reality itself. Adults who encountered him often remarked not only on his intelligence, but on the calm intensity with which he observed. Rather than interrupting conversation with childish impatience, he listened, stored details, and returned later with questions that startled his elders with their depth. If a scholar explained the phases of the moon, the boy would ask how these phases appeared from lands beyond Khwarezm. If someone spoke of distant cities, he wanted to know how long their day was, what languages people spoke, what stars appeared above their horizon. This urge to compare, not just to learn, but to place knowledge into a broader map, became the foundation of his later comparative studies in astronomy, geography, and world religions. Even in childhood, his mind did not rest within a single reference point. It expanded outward constantly. Nature itself functioned as his first tutor. The deserts around Khwarezm gave him clear skies for astronomical measurement. The river plains showed the dependency of life on climate and soil. Shifting trade routes brought news, tools, languages, and ideas from distant places. Every new stimulus fed his imagination. A foreign merchant describing Indian temples, a traveler recounting Greek scientific theories preserved in Arabic, a local artisan demonstrating how to align bricks perfectly. All these fragments ignited questions that no single discipline could answer. Al-Biruni's curiosity moved across boundaries freely. He did not distinguish mathematics from geography, astronomy from cultural history, or language from science. Instead, he sensed that all fields of knowledge were threads of one fabric. His childhood intelligence, therefore, was not merely sharp. It was expansive, integrative, and fearless. By adolescence, he had already developed the habits that would define his life's work. Observe first, calculate second, conclude only after evidence has been tested. While many young scholars memorized texts from authority, Al-Biruni trained his intellect through the world itself. His curiosity made him restless with easy answers. His intelligence turned wonder into method. Together, they built the foundation of a mind that would later measure the circumference of the earth with astonishing precision, study cultures without prejudice, and approach knowledge as a limitless landscape rather than a closed system. His childhood did not simply reveal his potential. It revealed the blueprint of the scholar he would become. Al-Biruni's early education unfolded in an environment where mathematical learning was not a luxury, but a necessary tool for astronomy, land measurement, and calendar regulation. In Khwarezm, scholarly families and court-backed teachers introduced promising students to arithmetic at a young age, often through practical problems, dividing inheritances, calculating market weights, or determining distances from basic measurements. Al-Biruni quickly moved beyond these elementary exercises. He showed a striking talent for handling ratios, geometric shapes, and the idea of proof. Rather than being satisfied with knowing how to calculate, he wanted to understand why certain numerical relationships always held true. This desire pushed his teachers to introduce him early to Euclidean-style geometry and the tradition of Greek mathematics, as it had been translated into Arabic, giving him a foundation that was far more rigorous than what most students of his age received. As he advanced, mathematics became the language through which he interpreted the natural world. Teachers trained him in basic algebra and geometry, not as isolated subjects, but as tools for astronomy and geography. He learned to think in terms of angles, arcs, and chords, which later allowed him to design experiments for measuring the Earth's radius and determining latitude. Trigonometric ideas, still developing in the Islamic world, were introduced to him through astronomical handbooks and observational practices at local observatories. Al-Biruni absorbed these methods with unusual speed. Where many learners treated formulae as things to memorize, he grasped them as condensed descriptions of the sky's behavior. His early notebooks, now lost but described in later biographical traditions, likely contained careful numerical tables, rough diagrams of the heavens, and attempts to reconcile theory with direct observation, all of which trained him to treat mathematics as both an abstract discipline and a practical instrument. Parallel to his mathematical formation, Al-Biruni's education in languages laid the groundwork for his later role as a comparative scholar. Arabic, the language of scholarship and religion in his region, was his primary vehicle for study. He learned grammar, rhetoric, and vocabulary, not only to read religious texts, but also to access scientific works translated from Greek, Syriac, and earlier Persian sources. Mastery of Arabic allowed him to enter the intellectual mainstream of the Islamic world, where commentary, critique, and original treatises circulated widely among scholars from Andalusia to Central Asia. However, he did not stop there. Being a native of Khwarezm meant he was also exposed to the local Iranian dialect, giving him access to pre-Islamic Persian traditions, oral histories, and technical terms not always fully captured in Arabic translations. This bilingual environment sharpened his awareness that single words in different languages rarely map perfectly onto one another, a realization that would later shape his comparative studies of vocabulary, religion, and science. As his reputation grew, Al-Biruni deliberately expanded his linguistic skills to deepen his scientific and cultural understanding. Even in his youth, he showed an unusual interest in how different peoples named the same stars, months, or mathematical concepts. This curiosity led him to gather glossaries, calendars, and place names in multiple tongues. When he later came into closer contact with Indian scholars, he devoted himself to learning Sanskrit so that he could read philosophical and scientific works without relying on second-hand summaries. The roots of that achievement lay in his early training. From the beginning, language for him was not just a means of communication, but a key to entire intellectual worlds. Each new language opened another archive of ideas, and his mathematical discipline gave him the precision needed to compare them carefully rather than mixing them carelessly. By the time Al-Biruni reached early adulthood, his education in mathematics and languages had fused into a single, powerful habit of mind. Mathematics gave him a strict standard of proof. Languages gave him a broad field of evidence. He approached texts with the same precision he brought to numerical calculation, checking claims against observation, cross-referencing terms across cultures, and refusing to accept authority without verification. This combination allowed him, later in life, to critique astronomical models, reconcile differing calendars, and compare religious practices with an objectivity rare for his time. The boy who once traced shadows and memorized declensions matured into a thinker for whom numbers and words were twin instruments, enabling him to measure both the shape of the earth and the shape of human thought with remarkable clarity. Al-Biruni's scientific mindset did not arise from a single teacher or a single discipline. It formed at the intersection of several habits that he cultivated early: careful observation, numerical precision, and a constant willingness to question received opinion. From a young age, he realized that authorities disagreed with one another. Greek astronomers, Persian scholars, Indian savants, and religious thinkers often offered conflicting explanations for the same phenomena. Instead of choosing one side and defending it, he took a different path. He asked how each claim could be tested. This instinct, to treat every assertion as a hypothesis rather than a final truth, became the backbone of his intellectual character. The world for him was not a commentary to be memorized, but a field of problems waiting to be measured, compared, and resolved. A key element of this mindset was his devotion to quantification. Where many scholars were satisfied with qualitative descriptions, the star is brighter, the day is longer, the land is far. Al-Biruni wanted numbers. He designed and improved instruments to determine angles, distances, and times. He used geometry not merely as an abstract game, but as a tool to extract precise information from the sky and the earth. In his later works, he would calculate the Earth's radius, compare longitudes of different cities, and examine the inclination of the ecliptic, all through methods that relied on measurable data rather than speculation. This mathematical discipline trained him to distrust vague statements. If something could not be expressed in terms that allowed calculation, he treated it as incomplete knowledge. Another defining feature of his scientific temperament was his love of comparison across cultures. Al-Biruni did not confine himself to the intellectual heritage of one civilization. When he encountered Indian, Greek, or other scientific traditions, he did not accept or reject them wholesale. Instead, he placed them side by side. He compared astronomical tables, calendar systems, geographical descriptions, and even religious cosmologies, noting where they agreed and where they diverged. This comparative method served two purposes. First, it revealed hidden assumptions, ideas that one culture took for granted, another might reject or never consider. Second, it allowed him to infer which statements were more likely to be accurate, especially when independent traditions, with no direct contact, arrived at similar measurements. In this way, his scientific mindset was inherently international. Truth, for him, was not the property of any one people. Crucially, Al-Biruni combined intellectual rigor with a rare willingness to admit uncertainty. He did not feel compelled to provide an answer where evidence was lacking. In his writings, he often distinguishes between what he has checked personally, what he has computed from reliable data, and what he reports on the basis of others' testimony. This layering of confidence levels, clearly marking the difference between direct observation, calculation, and hearsay, shows a self-awareness that modern science would later formalize. He did not consider it a weakness to say, "This is not yet clear," or "I report this without endorsing it." On the contrary, he regarded honesty about the limits of knowledge as part of intellectual integrity. Finally, his scientific mindset was deeply ethical in tone. For Al-Biruni, the pursuit of knowledge was not just a means to technical power, it was a way of honoring the order built into creation. Precision, fairness to other cultures, and care in handling sources were, in his view, moral obligations. This ethical dimension protected his work from both arrogance and prejudice. He could analyze the practices and beliefs of other peoples without contempt, even when he disagreed with them, because he saw himself as a recorder and evaluator, not a judge sitting above them. In this synthesis of critical method, mathematical exactness, cultural openness, and moral seriousness, Al-Biruni's scientific mindset took its distinctive shape, centuries ahead of what we now call the modern scientific attitude, yet already embodying many of its essential features. When Al-Biruni entered the circle of scholars gathered at the Khwarezmian court, he stepped into a structured yet remarkably lively intellectual environment. Under the Ma'munid rulers, the capital, often identified with Gurganj, Urgench, hosted an academy where astronomers, physicians, theologians, mathematicians, and linguists worked side by side. This was not a vague, learned atmosphere, but a concrete institution supported by rulers who wanted their court to rival the prestige of Baghdad and Bukhara. Al-Biruni, still relatively young, was drawn into this network as a promising mathematician and astronomer. In the academy's halls and observatory platforms, he had regular contact with senior scholars who critiqued his ideas, shared instruments, and debated technical problems with a seriousness that gave his developing talent both direction and discipline. Life inside this academy followed a rhythm shaped by observation and discussion. Days were often organized around specific projects, recording the positions of planets, refining astronomical tables, checking eclipses against predicted times, or recalculating the length of the year. Al-Biruni took part in these group efforts, learning how to coordinate theory with joint measurements, how to correct for instrumental errors, and how to reconcile conflicting data. Shared work meant shared responsibility. If the Academy announced a new value for a celestial parameter, the entire group's credibility was at stake. This collaborative pressure pushed him to be meticulous, not only in his own calculations, but also in questioning and verifying the results of others. In this setting, he learned that precision is not just a personal virtue, it is the glue that holds a scientific community together. The Academy was also a place where disciplines intersected constantly. Mathematicians consulted physicians about the timing of treatments based on planetary positions. Theologians argued with astronomers about the structure of the heavens. And geographers asked for more accurate coordinates to describe distant lands mentioned in travelers' reports. Al-Biruni thrived in this cross-disciplinary atmosphere. problems that began as purely technical often led him into broader questions. A discrepancy in astronomical tables raised issues about calendar reform. A discussion of climate and latitude opened into reflections on human customs and languages. Within Khwarezm's academy, he learned to treat no field as isolated. Astronomy was linked to geography, geography to ethnography, ethnography to comparative religion. This habit of connecting apparently separate domains became one of the hallmarks of his mature work. During his years at the academy, Al-Biruni also began to compose independent treatises that bore the stamp of this institutional training. He wrote on astronomical instruments, theoretical celestial mechanics, and mathematical methods with a clarity that reflected repeated explanation and defense of his ideas before peers. The critiques he encountered in seminars and informal discussions forced him to sharpen definitions, explain assumptions, and distinguish carefully between what had been directly measured and what was extrapolated. In these writings, we see not only a gifted individual, but the imprint of a collective intellectual culture. Footnotes that acknowledge other scholars' results, respectful disagreements, and careful comparison of rival models. The Academy did not merely provide him with resources, it shaped his style of argument and his standards of evidence. The political fate of Khwarezm would eventually scatter this community when the region fell under the power of Mahmud of Ghazni, but the habits Al-Biruni formed there never left him. Even after he was taken to Ghazni and began his famous studies of India and other lands, he continued to think like a member of a research circle rather than a solitary genius. He cited colleagues from Khwarezm, reused and refined techniques first tested under its clear skies, and carried with him the memory of a court where rulers believed that prestige depended on knowledge as much as on armies. The years in Khwarezm's academy were thus foundational. They transformed a talented youth into a disciplined researcher, taught him how a community of inquiry operates, and gave him a model of scholarly life that he would recreate in new settings for the rest of his career. Al-Biruni's scientific legacy rests prominently on his work in astronomy, geometry, and trigonometry, three fields he treated not as separate sciences, but as interdependent tools for understanding the physical structure of the universe. Astronomy was the core of his research agenda, providing the problems that geometry helped visualize and trigonometry helped solve numerically. He studied planetary paths, the inclination of the ecliptic, the timing of eclipses, and the changing length of daylight across different latitudes. But unlike many astronomers of his time, he saw observation as only half of the task. Precise measurement must be paired with rigorous mathematical analysis. His astronomical work therefore grew in dialogue with geometry. Every sighting required spatial interpretation. Every planetary model demanded quantified angles and distances. In this way, the sky became a vast geometric diagram stretched overhead, inviting calculation instead of awe alone. One of his breakthroughs came from his determination to create exact rather than approximate methods. Earlier scholars often relied on traditional values inherited from Greek or Indian astronomy. Al-Biruni, however, insisted on recalculating them. He measured the Earth's radius using trigonometric principles applied to a mountain elevation, an experiment renowned for its simplicity and precision. By observing the dip of the horizon from a high point and applying geometric reasoning, he derived a value astonishingly close to the modern figure. This was astronomy transformed into earth science, showing that celestial geometry could be used to measure the planet itself. His confidence in experimental trigonometry later enabled him to design tables and formulas that improved astronomical predictions beyond what earlier traditions had achieved. In trigonometry specifically, Al-Biruni stands as one of the great systematizers before the later European revival. He preferred sines over chords, a mathematical shift that simplified calculations dramatically, produced detailed sine, cosine, and tangent tables, and clarified relationships between the 6 trigonometric functions in a self-contained framework. For him, trigonometry was not just a tool for astronomers, it was a language for describing curved surfaces, angular distances, and the geometry of the sphere. He applied it to finding Qibla directions for prayer, calculating time from solar altitude, and determining longitudinal differences between distant cities. He also introduced methods to compute the Earth's meridian arc, laying conceptual groundwork for geodesy centuries before it became a formal discipline. Geometry for Al-Biruni was the theoretical skeleton behind his astronomy and trigonometry. He studied Euclid deeply, but did not treat geometry as static theory. He used it dynamically to model eclipses, reconstruct planetary orbits, and solve complex problems of spherical astronomy. He understood conics, projection methods, and the geometry of shadows, which helped him determine the height of distant objects without physically approaching them. His ability to turn geometry into applied instrument making led to improvements in astrolabes, quadrants, and sighting devices. These inventions, rather than mere abstract speculation, are evidence of a mind trained to move between concept and mechanism, between theorem and observation. By the end of his career, Al-Biruni had woven astronomy, geometry, and trigonometry into a single intellectual fabric. The movement of stars became a geometric structure. Geometric relationships became trigonometric formulas. Trigonometry became a tool to measure the curvature of earth and sky. Few scholars before him united theory and measurement with such fluency. His work did not merely advance each field, it demonstrated how a scientific mind could fuse them into one continuous method. The cosmos, for him, was not mystery to be accepted, but a system to be measured, calculated, and understood. The stability that had nurtured Al-Biruni's early scholarship in Khwarezm did not last. As the 10th century drew toward its close, the political landscape of Central Asia shifted under the pressure of expanding empires. The Ghaznavid ruler, Mahmud of Ghazni, sought to extend his authority over the wealthy and intellectually active Khwarezmian state. The Mamunid dynasty, which had supported scholars and fostered scientific inquiry, became a strategic target. What began as a political maneuvering eventually erupted into full military confrontation. When Mahmud conquered Khwarezm, the scholarly community that had once flourished in its academies was scattered. Al-Biruni, like many of his colleagues, found himself caught between competing powers, valued for his intellect, yet vulnerable to political force. The fall of Khwarezm marked a turning point not only for the region, but for Al-Biruni personally. He was not permitted to remain an independent scholar in his homeland. Instead, he was taken under Ghaznavid authority, almost certainly against his will, and brought to Ghazni. Though later generations sometimes softened the narrative, the circumstances were harsh. Al-Biruni did not migrate freely in search of knowledge. He was removed from his cultural base by conquest. Yet, in being uprooted, he carried with him the intellectual habits, methods, and memories of the Khwarezmian Academy. Forced migration thus became an unexpected bridge, transplanting a mind trained in a specific scholarly community into a new imperial context. The trauma of displacement did not break him. It redirected the trajectory of his scientific career. In Ghazni, Al-Biruni lived under a ruler known for military ambition rather than philosophical patience. The Ghaznavid court was wealthy, powerful, and expansionist, particularly focused on campaigns into the Indian subcontinent. For a scholar accustomed to open intellectual exchange, this environment was at first restrictive, yet his captivity gave him new access to cultures, languages, and scientific traditions beyond Khwarezm. When Mahmud's armies moved into northern India, Al-Biruni accompanied them, not as a soldier or propagandist, but as a scholar-observer. His forced proximity to conquest became an unexpected doorway into the intellectual world of India. Instead of mourning what he had lost, he immersed himself in Sanskrit, studied Hindu cosmology, and gathered astronomical and mathematical knowledge that later formed the foundation of his Kitab al-Hind, one of the most remarkable works of cross-cultural science ever written. The forced migration also taught Al-Biruni to intellectualize displacement rather than despair under it. Removed from his homeland, he responded not by retreating into bitterness, but by expanding the scope of his inquiry. He became more comparative, more critical of cultural bias, and more committed to empirical verification. Where he once compared Greek and Persian knowledge, he now added Indian systems to the triangulation, refining his scientific worldview into a global framework centuries ahead of its time. Political upheaval took him out of Khwarezm, but it pushed him deeper into the world. His intellect, shaped in one center of learning, adapted itself to another. Instead of collapsing under the weight of exile, he turned dislocation into discovery. In this sense, Al-Biruni's forced migration demonstrates the resilience of a scientific mind. His journey was painful, unchosen, and shaped by imperial domination, yet it intensified rather than diminished his scholarship. Political change uprooted his life, but it broadened his horizon, transforming a regional scholar into a global one. While courts and empires rose and fell around him, his work continued with the same rigor that defined his youth. Through adversity, he became not simply a product of Khwarezm, but a traveler between worlds, an observer who demonstrated that knowledge may be displaced, but it need not be destroyed. Al-Biruni's relocation to Ghazni marked a dramatic shift in his intellectual life. Removed from the familiar scholarly environment of Khwarezm, whether through political pressure, military defeat, or forced transfer, he found himself inhabiting the court of Mahmud of Ghazni, where knowledge served empire as much as it served inquiry. Ghazni was not merely a new capital, it was a center of military ambition, economic wealth, and cultural blending. Here, Al-Biruni entered a world where the priorities of rulers were shaped by expansion and conquest, rather than the quiet patronage of scholarship. Yet within this environment, he identified opportunities. Instead of retreating inward or lamenting displacement, he surveyed his surroundings with the same analytic discipline that defined his scientific work. The landscape was different, but the tools of inquiry were the same, and he continued to use them with astonishing clarity. What distinguished Ghazni was its international character. Soldiers, diplomats, administrators, translators, merchants, and scholars flowed through its gates, carrying with them languages, cosmologies, mathematics, and geographic memories from many lands. Al-Biruni, now positioned at the heart of an imperial court that touched multiple frontiers, gained access to intellectual materials that had never circulated in Khwarezm. He studied Sanskrit through direct contact with Indian pandits, captured or welcomed into the Ghaznavid sphere of influence. He conversed with theologians from Persia and jurists from Iraq. He corresponded with scholars in Rai, Bukhara, and Nishapur. Ghazni thus became a crossroads rather than a prison, an unplanned but fertile site where the fragments of world knowledge could be compared, measured, and synthesized. In this new network, Al-Biruni's method of inquiry evolved even further. Dialogue with Indian philosophers pushed him to refine his approach to comparative science. He did not merely document Indian astronomy, mathematics, or religious practice. He placed them next to Greek and Islamic systems, testing each against observation and logic. Where ideas converged, he saw confirmation. Where they diverged, he interrogated assumptions, cultural vocabulary, and methodological differences. This comparative triangulation, Khwarezmian, Greek, Islamic, and Indian, was only possible because his relocation forced him into contact with knowledge traditions that previously existed at a distance. Displacement, though political in origin, became intellectual expansion in consequence. Ghazni also introduced him to patrons who valued his work not only for scholarship, but for practical application. His astronomical calculations were used for calendar reform and geographic measurement. His mathematical insights supported efforts to map conquered territories. His linguistic research aided intercultural negotiation and translation. This integration of science with administration gave him a new kind of influence, less scholarly in atmosphere, but more consequential in real policy. The scholar of Khwarezm became the intellectual strategist of a trans-regional empire. He did not abandon his scientific independence, but learned to navigate a system where knowledge flowed through power. His relocation thus reshaped his audience, expanded his materials, and amplified the scope of his inquiry. In Ghazni, Al-Biruni became more than a scholar. He became a mediator between civilizations. No longer rooted in a single court or tradition, he inhabited an intellectual network that stretched across borders, languages, and belief systems. Even if the journey began in conquest, it matured into dialogue. From that position, he built the foundation for the works that would define him. Scientific treatises that spoke across cultures rather than within one. Through relocation, he gained not only a new home, but a larger intellectual horizon, one vast enough to hold the entire world within a single method of inquiry. The relationship between Al-Biruni and Ibn Sina, Avicenna, stands as one of the most remarkable intellectual interactions of the medieval Islamic world. Both men emerged from the scholarly landscape of Central Asia at roughly the same time, and their reputations spread widely during their own lifetimes. Yet, despite their shared brilliance, they approached knowledge from fundamentally different angles. Ibn Sina built a philosophical system grounded in metaphysics and Aristotelian logic, seeking to explain the universe through hierarchical reasoning and theoretical synthesis. Al-Biruni, on the other hand, preferred empirical verification, mathematical measurement, and experimental observation. Their encounter therefore brought together two different models of knowledge, the philosopher and the scientist, the system builder and the empiricist. This mix produced moments of collaboration, but also sparked tensions that reverberated through their writings. Their rivalry became most apparent in the field of natural philosophy, especially in questions related to cosmology, physics, and the nature of time. Ibn Sina leaned heavily on Aristotelian principles, arguing that certain truths could be known through pure intellect, regardless of empirical appearance. Al-Biruni rejected this approach, insisting that philosophical claims must be tested against observation. When Ibn Sina wrote about motion and the composition of matter, Al-Biruni challenged assumptions that lacked measurable proof. He questioned, for example, the necessity of celestial spheres and the premise that heavenly bodies must move in perfect circles. Ibn Sina defended classical cosmology, while Al-Biruni pressed for mathematical models grounded in observation rather than tradition. Their correspondence on these topics shows not hostility, but a rigorous exchange in which each pushed the other to refine argument, evidence, and definition. Yet, rivalry did not exclude respect. Al-Biruni valued Ibn Sina's mastery of logic and medicine, often citing his ideas even while disagreeing with them. Ibn Sina, likewise, recognized Al-Biruni's mathematical brilliance and sometimes modified his own views when confronted with strong empirical reasoning. They shared knowledge of astronomy, medicine, and metaphysics, sometimes trading manuscripts and critiques like sparring partners testing one another's intellectual defenses. Their disagreements were sharp, but rarely personal. Each treated the other as a worthy equal, a counterweight capable of preventing intellectual complacency. In this way, rivalry became a catalyst rather than an obstacle. It forced both men to articulate their ideas with greater precision, depth, and clarity. Their collaboration was most visible in the exchange of questions and responses preserved in later sources. Al-Biruni would pose detailed scientific challenges, sometimes dozens at a time, pressing Ibn Sina to justify philosophical principles that seemed disconnected from observable data. Ibn Sina replied with long, dense analyses, defending metaphysics on terms that Al-Biruni found insufficiently grounded. In response, Al-Biruni would refine the question, demand empirical reasoning, or propose experimental tests. What emerged was not a unified theory, but a dual vision of intellectual inquiry, one emphasizing reason as the path to truth, the other insisting on measurement and verification. Their dialogue demonstrates a rare moment in history when two towering minds confronted one another openly, neither submitting, neither collapsing into dogma, both driven by a shared desire to understand the universe. The legacy of their rivalry extends far beyond their own lifetimes. Later, scholars drew from each of them in different ways. Philosophers leaned toward Ibn Sina's conceptual architecture, while scientists and mathematicians inherited Al-Biruni's methods of verification and cross-cultural comparison. Together they represent two pillars of Islamic intellectual history, one theoretical, one empirical. Their relationship shows that scientific progress does not require unanimous agreement. It thrives on disciplined disagreement, well-reasoned challenge, and the willingness to test ideas rather than worship them. In the tension between Al-Biruni and Ibn Sina, we see a portrait of knowledge evolving through debate, a meeting of minds that sharpened both without diminishing either. Al-Biruni's arrival in India was not a simple scholarly expedition, but the result of his forced relocation under the Ghaznavid campaigns. Yet, once present on Indian soil, he turned a circumstance shaped by war into one of the most extraordinary intellectual engagements in history. Instead of remaining an observer at a distance, he immersed himself deeply in Indian science, religion, and philosophy. He recognized early that the intellectual traditions of India could not be understood through hearsay or through translations filtered by cultural prejudice. To comprehend the mathematical astronomy of Aryabhata, the philosophical structure of the Upanishads, or the logic of Brahmin ritual practice, he needed direct access to the original language. Thus he undertook the demanding task of learning Sanskrit, a decision that would transform his research and extend the boundaries of comparative knowledge in the medieval world. Learning Sanskrit opened a new intellectual universe for Al-Biruni. Unlike scholars before him, who encountered Indian ideas indirectly, he read astronomical treatises, philosophical texts, and linguistic grammars firsthand. He studied works such as the Brahmasphutta Siddhanta, Surya Siddhanta, and Panchanga calendar systems, not as second-hand information, but as primary scientific documents. Through these readings, he discovered mathematical innovations unique to India, trigonometric identities, astronomical parameters, and refined numerical methods. He was particularly struck by Indian use of sine tables and their distinct approach to planetary motion. This encounter challenged his assumptions formed through Greek and Islamic astronomy, prompting a method of comparison rather than superiority. Instead of judging, he asked, "How do Indian models handle measurement? Where do they succeed? Where do they diverge?" Through such questions, he became one of the first scholars to treat scientific traditions as parallel rather than hierarchical. His research extended beyond mathematics and astronomy into culture, geography, religion, and philosophy. Al-Biruni spent years interviewing Brahmin scholars, observing ritual practice, mapping Indian rivers and mountain ranges, and recording linguistic structures with scientific neutrality. He studied Indian cosmology, the cycle of yugas, the doctrines of karma and moksha, and the logic of Hindu metaphysics, with the same precision he applied to planetary calculations. His goal was understanding, not conversion or criticism. In his monumental Kitab al-Hind, he explicitly states that he does not write to praise or to condemn, but to describe accurately so that one civilization may understand another without distortion. This impartiality set him apart from most medieval writers, creating a text that remains a masterpiece of ethnographic science, cultural sensitivity, and intellectual fairness. The encounter with Sanskrit did more than broaden his knowledge. It reshaped his method. By comparing Indian science with Greek, Persian, and Islamic data, he developed a framework that anticipated modern comparative methodology. He created astronomical tables that cross-referenced multiple traditions, analyzed differences in planetary constants, and identified where observational error or conceptual bias produced divergent results. India showed him that scientific truth could not be monopolized by a single culture, and that verification must come from testing ideas across languages, climates, and worldviews. In studying India, Al-Biruni became not just a recorder of knowledge, but a bridge between civilizations. His engagement with Sanskrit transformed him into the first truly global scientist, a scholar for whom borders were not boundaries, but places where understanding could expand. Kitab al-Hind was not simply a book. It was the outcome of years of direct observation, linguistic study, and intellectual dialogue across civilizations. Al-Biruni did not write it from second-hand accounts or through the distorted lens of conquest. Rather, he built it through long conversations with Indian scholars, through reading Sanskrit texts in their original form, and through comparing Indian scientific conclusions with those of Greek and Islamic traditions. His aim was clarity, not persuasion. He understood that India held a scientific heritage equal in complexity to the Hellenistic one, and refused to reduce it to exotic curiosity. The writing of Kitab al-Hind therefore became an act of meticulous translation, not merely of language, but of worldview. He entered the intellectual interior of another civilization and attempted to render it visible without distortion to readers who had never seen it. The book is structured like an inquiry. Concept by concept, field by field, he describes Indian astronomy, mathematics, cosmology, ritual practice, medicine, geography, and philosophy. He quotes Sanskrit verses, explains technical vocabulary, and even reconstructs Indian calculations, sometimes agreeing with them, sometimes identifying points that required further verification. In doing so, he treated Indian knowledge not as foreign, but as parallel science, a system capable of standing beside the Greek Islamic tradition on equal footing. This was unprecedented. Medieval scholars often judged other traditions through preconceived frames, declaring them correct only when they matched familiar doctrines. Al-Biruni reversed this approach. He built a method that allowed two civilizations to look at one another scientifically, not hierarchically. Kitab al-Hind became the first large-scale study in world intellectual history to compare science across cultures without forcing the results into a single narrative. He also demonstrated that cross-cultural science requires emotional discipline. In the introduction of the work, Al-Biruni warns the reader that the customs he describes may appear strange or irrational when compared to Islamic norms. He insists that the scholar must suspend judgment in order to see clearly. This was more than cultural tolerance, it was methodology. He distinguished between fact and interpretation, between what Indians believed and why they believed it, between observed reality and symbolic meaning. His discussions of reincarnation, cosmological cycles, or numerical symbolism are never mocking. They are explanatory, analytical, and often sympathetic. In this way, Kitab al-Hind becomes not only a scientific compendium, but a manual in how to observe another civilization without intellectual conquest. The scientific value of Kitab al-Hind lies in its comparative precision. Al-Biruni produced astronomical tables aligning Indian planetary constants with those of Ptolemy and Islamic astronomers, tracked differences in trigonometric methods, and proposed corrections where independent evidence suggested more accurate values. He compared calendars, units of measure, and geographic data with mathematical scrutiny. When he found agreement across traditions, he marked it as strong evidence. When traditions diverged, he analyzed whether the cause was observational error, geographical difference, or theoretical assumption. This form of cross-checking made his book one of the earliest examples of what we now call scientific peer review, performed not among individuals, but among civilizations. In writing Kitab al-Hind, Al-Biruni achieved something many eras failed to imagine. He showed that science does not belong to one culture, one language, or one faith. Knowledge, when observed carefully and compared fairly, becomes a bridge rather than a boundary. His book preserved Indian science for the Islamic world, and in doing so preserved a heritage that might otherwise have remained misunderstood or unseen. Through Kitab al-Hind, Al-Biruni proved that the pursuit of truth expands only when we learn to listen across worlds, and when we allow another civilization not simply to be studied, but to speak. Al-Biruni treated geography not as a descriptive art, but as a quantitative science. Where earlier scholars mapped regions through travel stories and estimated distances by memory, he insisted that geographical knowledge must be anchored in measurement. His work began with an idea simple yet revolutionary. The Earth could be studied directly, its size calculated through geometry rather than inherited belief. To do this, he needed accurate latitude determinations, horizon measurements, and a mathematical model of Earth's curvature. Al-Biruni approached these challenges with the mindset of an experimental physicist centuries before the term existed. He designed instruments to sight the sun and stars, recorded the elevation of mountains and the dip of the horizon, and developed the theoretical framework to turn observation into planetary measurement. His most famous experiment, calculating the Earth's radius, stands as one of the clearest examples of applied trigonometry in the medieval world. Al-Biruni climbed a high mountain near Nandana, measured its elevation using geometric surveying, and determined the angle at which the horizon dipped away from the peak. With these two values, he applied a trigonometric formula that allowed him to compute Earth's radius directly. The result he produced was astonishingly accurate, deviating less than 1% from the value accepted today. What makes this achievement remarkable is not only its precision, but the method itself. He did not rely on assumptions or philosophical arguments, but on measurable geometric relationships. The Earth was not spherical because Aristotle said so. It was spherical because the horizon proved it mathematically. Geography for Al-Biruni extended beyond Earth's shape into mapping regions, measuring longitudes, and correlating climate with latitude. He compared daylight lengths across different cities, observed seasonal variations in shadow length, and constructed tables that linked astronomical data to terrestrial coordinates. He understood that geography was inseparable from astronomy. The position of the sun and stars could locate a city more reliably than any written itinerary. To determine longitude differences, one of the most difficult problems of his time, he proposed synchronized lunar eclipse observations across multiple locations. This idea, though technologically ahead of its age, illustrates his insistence that science must transcend politics, distance, and individual perception. Knowledge, for him, required coordinated global measurement. In the introduction of the work, Al-Biruni warns the reader that the customs he describes may appear strange or irrational when compared to Islamic norms. He insists that the scholar must suspend judgment in order to see clearly. This was more than cultural tolerance, it was methodology. He distinguished between fact and interpretation, between what Indians believed and why they believed it, between observed reality and symbolic meaning. His discussions of reincarnation, cosmological cycles, or numerical symbolism are never mocking. They are explanatory, analytical, and often sympathetic. In this way, Kitab al-Hind becomes not only a scientific compendium, but a manual in how to observe another civilization without intellectual conquest. The scientific value of Kitab al-Hind lies in its comparative precision. Al-Biruni produced astronomical tables aligning Indian planetary constants with those of Ptolemy and Islamic astronomers, tracked differences in trigonometric methods, and proposed corrections where independent evidence suggested more accurate values. He compared calendars, units of measure, and geographic data with mathematical scrutiny. When he found agreement across traditions, he marked it as strong evidence. When traditions diverged, he analyzed whether the cause was observational error, geographical difference, or theoretical assumption. This form of cross-checking made his book one of the earliest examples of what we now call scientific peer review, performed not among individuals, but among civilizations. In writing Kitab al-Hind, Al-Biruni achieved something many eras failed to imagine. He showed that science does not belong to one culture, one language, or one faith. Knowledge, when observed carefully and compared fairly, becomes a bridge rather than a boundary. His book preserved Indian science for the Islamic world. and in doing so preserved a heritage that might otherwise have remained misunderstood or unseen. Through Kitab al-Hind, Al-Biruni proved that the pursuit of truth expands only when we learn to listen across worlds, and when we allow another civilization not simply to be studied, but to speak. Al-Biruni treated geography not as a descriptive art, but as a quantitative science. Where earlier scholars mapped regions through travel stories and estimated distances by memory, he insisted that geographical knowledge must be anchored in measurement. His work began with an idea simple yet revolutionary. The Earth could be studied directly, its size calculated through geometry rather than inherited belief. To do this, he needed accurate latitude determinations, horizon measurements, and a mathematical model of Earth's curvature. Al-Biruni approached these challenges with the mindset of an experimental physicist centuries before the term existed. He designed instruments to sight the sun and stars, recorded the elevation of mountains and the dip of the horizon, and developed the theoretical framework to turn observation into planetary measurement. His most famous experiment, calculating the Earth's radius, stands as one of the clearest examples of applied trigonometry in the medieval world. Al-Biruni climbed a high mountain near Nandana, measured its elevation using geometric surveying, and determined the angle at which the horizon dipped away from the peak. With these two values, he applied a trigonometric formula that allowed him to compute Earth's radius directly. The result he produced was astonishingly accurate, deviating less than 1% from the value accepted today. What makes this achievement remarkable is not only its precision, but the method itself. He did not rely on assumptions or philosophical arguments, but on measurable geometric relationships. The Earth was not spherical because Aristotle said so. It was spherical because the horizon proved it mathematically. Geography for Al-Biruni extended beyond Earth's shape into mapping regions, measuring longitudes, and correlating climate with latitude. He compared daylight lengths across different cities, observed seasonal variations in shadow length, and constructed tables that linked astronomical data to terrestrial coordinates. He understood that geography was inseparable from astronomy. The position of the sun and stars could locate a city more reliably than any written itinerary. To determine longitude differences, one of the most difficult problems of his time, he proposed synchronized lunar eclipse observations across multiple locations. This idea, though technologically ahead of its age, illustrates his insistence that science must transcend politics, distance, and individual perception. Knowledge, for him, required coordinated global measurement. In the introduction of the work, Al-Biruni warns the reader that the customs he describes may appear strange or irrational when compared to Islamic norms. He insists that the scholar must suspend judgment in order to see clearly. This was more than cultural tolerance, it was methodology. He distinguished between fact and interpretation, between what Indians believed and why they believed it, between observed reality and symbolic meaning. His discussions of reincarnation, cosmological cycles, or numerical symbolism are never mocking. They are explanatory, analytical, and often sympathetic. In this way, Kitab al-Hind becomes not only a scientific compendium, but a manual in how to observe another civilization without intellectual conquest. The scientific value of Kitab al-Hind lies in its comparative precision. Al-Biruni produced astronomical tables aligning Indian planetary constants with those of Ptolemy and Islamic astronomers, tracked differences in trigonometric methods, and proposed corrections where independent evidence suggested more accurate values. He compared calendars, units of measure, and geographic data with mathematical scrutiny. When he found agreement across traditions, he marked it as strong evidence. When traditions diverged, he analyzed whether the cause was observational error, geographical difference, or theoretical assumption. This form of cross-checking made his book one of the earliest examples of what we now call scientific peer review, performed not among individuals, but among civilizations. In writing Kitab al-Hind, Al-Biruni achieved something many eras failed to imagine. He showed that science does not belong to one culture, one language, or one faith. Knowledge, when observed carefully and compared fairly, becomes a bridge rather than a boundary. His book preserved Indian science for the Islamic world, and in doing so preserved a heritage that might otherwise have remained misunderstood or unseen. Through Kitab al-Hind, Al-Biruni proved that the pursuit of truth expands only when we learn to listen across worlds, and when we allow another civilization not simply to be studied, but to speak. Al-Biruni treated geography not as a descriptive art, but as a quantitative science. Where earlier scholars mapped regions through travel stories and estimated distances by memory, he insisted that geographical knowledge must be anchored in measurement. His work began with an idea simple yet revolutionary. The Earth could be studied directly, its size calculated through geometry rather than inherited belief. To do this, he needed accurate latitude determinations, horizon measurements, and a mathematical model of Earth's curvature. Al-Biruni approached these challenges with the mindset of an experimental physicist centuries before the term existed. He designed instruments to sight the sun and stars, recorded the elevation of mountains and the dip of the horizon, and developed the theoretical framework to turn observation into planetary measurement. His most famous experiment, calculating the Earth's radius, stands as one of the clearest examples of applied trigonometry in the medieval world. Al-Biruni climbed a high mountain near Nandana, measured its elevation using geometric surveying, and determined the angle at which the horizon dipped away from the peak. With these two values, he applied a trigonometric formula that allowed him to compute Earth's radius directly. The result he produced was astonishingly accurate, deviating less than 1% from the value accepted today. What makes this achievement remarkable is not only its precision, but the method itself. He did not rely on assumptions or philosophical arguments, but on measurable geometric relationships. The Earth was not spherical because Aristotle said so. It was spherical because the horizon proved it mathematically. Geography for Al-Biruni extended beyond Earth's shape into mapping regions, measuring longitudes, and correlating climate with latitude. He compared daylight lengths across different cities, observed seasonal variations in shadow length, and constructed tables that linked astronomical data to terrestrial coordinates. He understood that geography was inseparable from astronomy. The position of the sun and stars could locate a city more reliably than any written itinerary. To determine longitude differences, one of the most difficult problems of his time, he proposed synchronized lunar eclipse observations across multiple locations. This idea, though technologically ahead of its age, illustrates his insistence that science must transcend politics, distance, and individual perception. Knowledge, for him, required coordinated global measurement. In the latter phase of his life, Al-Biruni turned increasingly toward the work of synthesis, gathering, refining, and organizing the immense body of knowledge he had accumulated across decades of research, travel, and cross-cultural study. By this time, he had produced treatises in astronomy, mathematics, physics, mineralogy, pharmacology, history, and comparative religion. But what distinguished his later years was not merely the volume of his writing, but the clarity with which he transformed complex material into structured reference works. He believed that knowledge was not complete until it had been rendered accessible to others through tables, diagrams, glossaries, and critical commentary. His later writings therefore became a monumental effort to preserve scientific method for future generations, ensuring that discoveries would not die with their discoverer. During this period, Al-Biruni no longer worked in a single discipline. Instead, he moved fluidly across fields, connecting observation with textual analysis, mathematics with medicine, and cosmology with geology. His Canon Mas'udi, a massive encyclopedia of astronomy and mathematical geography, stands as a testament to this integrative labor. It contains not only observations and calculations, but critiques of predecessors, modified planetary tables, and carefully reasoned arguments about the structure of the heavens. His later treatises on gemstones, pharmaceuticals, and minerals show the same pattern: empirical measurement paired with clear explanation, each topic examined with both scientific skepticism and patient precision. He no longer sought discovery alone. He sought coherence. Teaching also became central to his final decades. Al-Biruni never founded a formal school, but students, scholars, and officials frequently sought his instruction. He taught astronomy through demonstration rather than doctrine, showing learners how to use instruments, how to test star positions, how to identify observational error, and when to withhold judgment. In philosophy and religion, he emphasized comparison over refutation. Students were urged to read unfamiliar texts directly instead of relying on commentary. His lessons often began with a question, not an answer, encouraging critical thinking rather than memorization. Through this approach, he created a lineage not of disciples who repeated his words, but of thinkers who adopted his method, skeptical, quantitative, and globally informed. As age advanced, Al-Biruni continued to write, refine, and correspond. Even when his mobility declined, his intellectual energy remained unbroken. He reviewed earlier works, corrected manuscripts, expanded tables, and preserved new knowledge brought to Ghazni through scholars, merchants, and travelers. His final years show a mind not fading, but concentrating, turning experience into structure, turning inquiry into legacy. He left behind not merely books, but a method. Observe with care, measure with precision, compare without bias, and document without arrogance. His later life can therefore be understood as his final contribution to science, not as discovery, but as transmission. He had mapped the world. Now he ensured others could navigate it after him. The precise circumstances of Al-Biruni's death, like much of his private life, were not recorded in detail. What is known is that he continued writing and dictating research until his final days in the mid-11th century, likely around 1050 CE in Ghazni. Contemporary accounts describe him requesting that passages of geometry and astronomy be read aloud to him, even on his deathbed, an image that reflects a lifetime sustained not by power or wealth, but by intellectual hunger. His passing marked the end of one of the most extraordinary scientific careers the medieval world had ever produced. Yet in many ways, his death was only the beginning of his scientific afterlife, for the body of work he left behind continued to grow in influence long after he was gone. His legacy rests upon both the range and the method of his scholarship. Al-Biruni did not merely write in multiple disciplines, he transformed them. Astronomy, trigonometry, geodesy, mineralogy, pharmacology, ethnography, comparative religion, and history all bear his imprint. His calculation of Earth's radius, his cross-cultural astronomical tables, and his hydrostatic measurements of density show a rigor that anticipates modern laboratory science. Kitab al-Hind remains one of the earliest and most sophisticated works of scientific anthropology. The Canon Mas'udi stands as a reference text of mathematical astronomy. His mineralogical treatises reveal experimental precision rare before the modern era. Through this blend of empiricism, mathematics, and cross-cultural inquiry, Al-Biruni became a model of what a global scientist could be centuries before the term existed. His influence spread widely across the Islamic world, and later into Europe. Scholars in Persia, Central Asia, and the Ottoman Empire copied and commented on his works for generations. In the 12th and 13th centuries, translations of his astronomy and geography circulated through Baghdad, Cairo, and Andalusia. Latin translators of the Renaissance, confronted with his tables, his measurements, and his philosophical arguments, found in him a thinker who challenged Aristotle not by rhetoric, but by calculation. His methods of sampling, comparison, and verification became foundational to the scientific spirit that would later appear in European natural philosophy. He stood as a silent teacher to scholars who never met him, a figure rediscovered each time empiricism re-emerged as the beating heart of science. Most remarkably, Al-Biruni's legacy is not limited to discoveries. It is rooted in attitude. He taught that cultures must be studied from within, that languages must be learned rather than filtered, that observation must override inherited theory, and that measurement is a universal language capable of connecting civilizations. His work dissolves the idea of isolated scientific traditions. Greek mathematics, Indian astronomy, Persian instrumentation, and Islamic scholarship met in his mind and emerged as comparative, testable knowledge. In an age often divided by empire and faith, he demonstrated that truth expands through curiosity rather than conquest. In the final horizon of his legacy, Al-Biruni stands as more than a medieval polymath. He represents a scientific consciousness ahead of its time, global in scope, empirical in method, intellectually fearless. His death closed a life of inquiry, but his influence opened a path through which world science could evolve. He measured the earth, but more importantly, he enlarged the intellectual world itself.